it's not gotten any easier just because we're big or ZHA was famous. It doesn't mean we get clients who just dump in money and like it's not blue sky thinking as might be perceived. It is a lot of effort to really, in some cases, fight for. In other cases, convince people. In other cases, like going out, reaching out to new industry, and it's a place that offers a lot for young people to build a career. It's hard work, but like if you just, it is an environment enough that like people like us, and there are 400 of them, and we bounce ideas. So like nationality doesn't matter, where you came from doesn't matter, gender doesn't matter. What matters is if you're dedicated. And it's one of the few offices that give a lot of responsibility to young people. So for example, Dave and Vishu, they're like running a project literally, I mean they're 27 years old, right? Like, so it's it just, if you're up for taking responsibility and taking ownership, like it's a place that's ZHA's legacy to young people. Like she gave an environment that you could feel free with the burdens of having to fight the outside world, let's say. So I joined the company in 2007 to specifically start like a research R&D department or a group of people, let's say. At that time when I joined, I was only one person. For the first 1.5 years, I was one person, and then we had 2, and then 3. We grow more or less at one person a year. So we're now about 8 people in a company of 450. And I'm the oldest. That's the only reason, like, I'm in charge of the group. Like, it's not that I have any more skill or less skill. And it's a very fortunate thing that, as I said, like the company offers like young people to develop their architectural ideas and also interest in technology or art. So started it in 2007. There was never an explicit idea of what R&D meant in a company. And as I said, it allows, I just added these slides. This was what I was doing in India. Like my undergrad was entirely in AutoCAD. Like, you know, first thing you go out, measure everything of the site, take photographs, draw. I drew every single line in this drawing, measured every plan of the context, took photos, like something that like very familiar perhaps to most of you, right? And I was working with my father as well for a couple of years before I went to the AA to do my master's. So I don't have any background in computers or programming or anything digital. My background is more theoretical. I wanted to be a journalist. Just so happened to become an architect. So perhaps these kind of things are familiar to you, like, and this was one of the projects that I worked on with my father, kind of resort thing, and like there was obviously there was no 3D, so everything is like projections, cutting sections, and like all of these things. But then once like I did my master's at the AA and like, you know, joined the office, like you can see it's a similar background just being explored in like 3D tools, right? Like and this was a project that we did like maybe 2-3 years ago. It's under construction now in China. But you can see like the transition of the language, and that's what I mean, like ZHA allows young people to develop a career, meaning you develop your design language, your vocabulary, your construction technologies, like your own network of contractors and like all of these things. So in that sense, it's a big company of smaller companies, right? Like each team is like maybe 6-7 people. The biggest team is maybe about 35 people. But then they're doing like airports and stuff. So we generally tend to do smaller projects because we think that gives us more direct control over the outcome. We as in computation and design group. So this is what we're currently exploring: correlation of expressive capacities of geometry with construction and also local materials and how you can like use technologies, appropriate them in like different cultures, right? Like, and so I was hired to do a very specific thing, or at least I thought it was specific. They said it's an R&D group. Do you want to lead it? Like, okay. But then the first day in the office, like it's like chaos, right? Like no one gives a shit of who you are. No one even tells you where the files are because everyone's like so into their worlds. So as things go in the last 10 years, like every year we kind of think of like what does R&D mean in a company like ZHA, because everyone is a designer, everyone is researching, everyone is extremely talented, like from various parts of the world. Like so whatever little ego you might have when I joined, I was like 27. Whatever ego you might have at the age of 27 quickly evaporates, because you see everyone is like insanely talented and like still working 14 hours a day. So you're like, okay, we need to do something. So initially we just did like whatever came our way, like everything from like shoes, like we did design shoes, limited edition shoes for Lacoste, and so it was the same kind of design ideas that make a shoe as the master plan. So yesterday someone was asking, how do you think of scale? And so we don't. It's about relationships. It's about as I said, it's not about dimensions. It's more about associations and how things relate to each other. And it's a logic of creation of geometry, a logic of creation of spaces. So scale in that sense is not as relevant. I mean, it is relevant once you start making it into real buildings or real products. Then the technology has there are differences. And along the way, things we began to be more systematic. Initially, we weren't. We were just doing it intuitively and like whatever comes to our mind. Today, whatever is the flavor of the month. Oh, I like this tool. I like that tool. Apply it and see what comes out. 2-3 years into into our lives, like at ZHA, like we began to be more systematic. So this is a study for a set of towers without a project. So studying towers for the sake of towers. These then became chess pieces. Some became actual towers. Some became vases, so on and so forth. So it's like geometry. It's exploration of a vocabulary, meaning like the same way we learn to speak, and then you can speak science or you can speak art or literature or whatever. Like there is something which is independent of its purpose, which has value for the sake of exploration. So research in its own merit, right? So it's like kind of design research in that sense, which is very important. So we explored in the vertical geometries, let's say. How do they stand up? How do they behave? Like as it gets taller, what can we change? So it's, as Frank was saying, just because you want to make a 100-meter tower, you don't stack two 50-meter towers on top of each other, right? Like, so there are fundamental differences between a 100-meter tower and a 50-meter tower. So that's the kind of things that we're trying to explore. So these are 3D prints in our gallery. People think they are towers, but in our minds, they're just geometry and exploration of certain vocabulary, right? So as I said, some of them became towers, like, so whenever there are competitions and stuff, like, so we don't have to generate new ideas per project. We already have explored some things. So we take them and make them into buildings, for example. So in the last 9-10 years, like, we've done like a range of things. So this is a project that is, these are the two projects that are currently on site that we have had more input on. Like, this is entirely being run by our team. The bigger one, we are a part of like a team of 40 people. So, and you will see that, like, making drawings is not, it's not impossible. It's not something that we normally do, right? It just, we try to think of design and geometry independent of its representation. As it can be represented as 2D drawings, it can be represented as a movie, a 3D model, a physical model. Those are representations of an internal idea. So you might or might not see a certain consistency in the kind of work that we have done over the last 8-9 years as a team. So similarly, every other team in ZHA has explored a vocabulary, a method of getting it made, interfacing with clients. Yeah, so that's what I mean, that like you join as like young people, and like over time, like you try to grow as designers, as architects, and develop your own, and that, like, I'm extremely grateful to both ZHA and Patrick and everyone else, in that sense that, you know, as a young untested person from India, like, there was no reason why they would want to take a risk, but they did, and then therefore, you know, like it allows, like, the company is rich because of that risk taking, because lots of people say have been in the office for 10 years, 15 years, 20 years, like in charge of little teams, and that's why the company is diverse and it's rich. Even though in the public eye, in the public image, it's all the same. Like, it's all swoopy things. It's all irreverence to culture. It's irreverence to. It's not true. That's the image which we have to maintain. Otherwise, people don't take us seriously. Like, if we try to be polite, they will just run you over, right? So we are thick-skinned in that sense, but we're not arrogant, right? Like, so. Okay, so those are the range of kind of projects that we have contributed to, but our core focus as a research and development team is to concentrate on these two aspects of architectural knowledge, deliberate production of knowledge in this technology of design and construction, like we are doing now, like Maya modeling, Rhino, scripting, programming, all those are design technologies. Construction technologies like a robot, the CNC machine, laser cutter, brick making, like all of these are technologies of design and construction, but we are equally interested in deliberate production of knowledge related to conception of design. Like how, so we don't leave it to intuition, like say, we want to talk about it, like, and initially it will be crude, and then the more we talk about it, like the more systematically we can think about design, it also becomes a form of knowledge, right? Like design knowledge, concept, how you conceive of design and new novel applications is also a form of knowledge that we try to focus on. So it's not a kind of geeky, it's not a geek club, let's say, although we do a lot of technology aspects, we do a lot of mathematics, like a lot of art, a lot of, but essentially we want to be good architects, like, and grow as architects every day. So that's what we mean by technology of design and construction, things that you've been exposed to perhaps more. Modeling, scripting, like Grasshopper, machines, and so on and so forth. But this morning we also, you got a sense of like our interest in the other side of things, the conception of design, like how do you engage with these things productively to make architecture, right? And like many people have spoken about this distinction, usually people tend to focus on one more than the other. Like there are people who are very theoretical and they talk about architecture as like having social implication, environmental implications, and like less about the technology. And there are other people who focus more on technology, more on robots, performance, and all of these kind of things, and forget to talk about the conception of design. Like, so we want to be somewhere a good balance. Again, as I said, this is not a new set of distinctions. Like as I mentioned in the first introductory presentation, this distinction, perhaps at least in Western architecture, can be traced back all the way to a kind of famous debate between these two people. Does anyone know who these two guys are? Huh? Oh yeah, of course an Italian will know, right? So the younger person is Alberti, and the older person is Brunelleschi. Brunelleschi didn't care about like styles of architecture, he didn't care about proportion and all of this, he didn't want to talk about it, he wanted to talk about how to make stuff. He was like inventing machines, he was barely making any drawings, he was on site like getting stuff done, and he had like a kind of, and he was not an architect really, he was a goldsmith. And Alberti was like a kind of the father of architecture, let's say, like in this, like he perfected the drawing of the perspective, he invented like instruments to draw properly, accurately, and like these kind of, and he was interested in, so Brunelleschi built this, famously built this dome, like he invented, I think in the 15th century or so, he not only, he didn't concentrate so much on these drawings, but he was very much interested in like making machines to enable the easy construction of that dome. So what he invented there was a kind of gear mechanism so that the horse can go always in one direction, and by flipping a gear, the weight, the material can be transported up or down. So the horse doesn't need to go backwards, right? Like, so it's a differential gear mechanism that that he invented for the purpose of construction of a dome 100 meters up in the sky, right? So, and you can clearly tell this is Alberti, very distinct, and you can see, you can blame Alberti for all our troubles of drawing and dimensions and these kind of things, which again we are saying both are important. We more than the drawing aspects, Alberti was also very much concerned on the impact of buildings on urban spaces, like how putting a building in a public square is different from putting the same building in a lesser public place, and so on and so forth. So social implications of building was also, so in that sense Alberti was like a kind of architect's architect. So more about these kind of distinctions and things you can find Parametricism 2.0 edited by Patrick Schumacher, and a lot of people have contributed articles to this latest AD. You can perhaps find it online, or I don't know how it works over here. But there are various aspects about this new tools and new ideas of architecture, how various people are trying to tackle that. Okay. And I contributed an article to the same issue called Upgrading Computational Design. So the rest of the presentation is basically putting pictures to that article. So if you buy that book, you don't have to read my article, because I'm going to be talking about it now. So how do we go about producing knowledge deliberately, right? So explicitly, it's not like intuitively producing something and just dumping it on the server and say, oh, do whatever you want with it. We have to, as a research group in an architecture company, we have to deliberately produce architectural knowledge, and hopefully some of it is useful, or most of it is useful. So we divide like our work more or less into these 4 categories of, or lines of inquiry, or let's say avenues of work. One is systematically producing knowledge, like the tower studies that we did. Like, so someone else can reproduce that or make use of it. And the other is, unlike modernism, which wanted to completely cut itself off from everything historic, we want to re-engage with historic methods of construction, of drawing, of calculating structure, and even invention of machines and so, like, we want to re-engage with that tradition. And we're also pretty much focused on interdisciplinary collaborations. We always seek to work with people who are not architects, like whether it's mathematicians or musicians or sculptors or product designers, or at the early stage of a design, we try to engage with them. And lastly, we see a deep symbiosis between academics and profession. ZHA herself was teaching in Yale, in Vienna, and then famously was deeply, she taught also at the AA initially, and she used to spend way more time with students than her own employees. She barely cared for spending time talking about projects, but if a student came by, she would clear out her schedule to chit chat with. So that's a spirit that permeates to a deep extent in our work. Like, so that's one of the reasons why we do these kind of workshops, to actively engage, and not only to say, this is one way of doing it, but for both directions. Like, so every workshop we do, when we go back, like, it does affect things that we do. We can't explicitly say this happened because of this workshop, but over time it does accumulate, let's say. So systematic generation of knowledge basically is something like this, right? Like, on the one hand, you're producing geometries and spatial ideas by starting with the simplest and then slowly exploring it further and further and further. And on the other hand, you're also applying analytical methods to understand what you've just drawn. So analysis is not only for you to make a building stand up. It's not the engineer's job only. You as a designer can do that as well. So you can analyze, okay, I just drew this, like, how is curvature changing across the surface? You can analyze, like, how is light reflecting off of it? Or you can analyze, like, what are the spatial opportunities that a certain kind of geometry provides, and so on and so forth. So you can then build little tools to help you analyze what you have just done, right? So two aspects of systemic generation of knowledge. You are disciplined in your production of geometry and of architectural design, and you're also systematically improving your intuition by using analytical tools. Okay. So incidentally, those colors represent. What do you think it represents? Topography. The right one, I think it's the light.
The red represents the.
This is geometry, right? This is roof studies of roof forms, like pitch roof. What do you think these colors represent? Intention. Forces. What else?
Performance.
Of. What? No?
It's like how steep the curvature is.
Yeah. In a way, it is related to how steep the curvature is. It's kind of tracing how fast the water will run off. So that's a designer intuition of structure, right? So if you drop water on a surface, it will run off and collect in areas. More or less, forces tend to do that. So in areas of steep curvature, like forces tend to travel faster through down, and if it is shallow curvature, it collects into a pool. And so when there's less curvature, that's why you need deeper material. It's not one-to-one, but it gives us enough intuition about this. If it was about forces, like as designers, we would understand less about it, right? Like if it was a structural analysis, it's like, what do those numbers mean? I don't know. But when you say it is about like water, how water flows off of a surface, everyone can imagine that, like, right? Yeah, so some of these things you already seen, like, we're interested in like new technologies of design and construction. And we're also, sometimes we make our own tools, sometimes we use tools that other researchers are making in various parts of the world, Grasshopper, so on and so forth, right? Like this, from ETH all the way to the US, whatever, like internet is our world, so there's no point reinventing the wheel if there's already a tool that does it, like we just take it and use it. And many times we also write our own tools. In this case, while we are modeling, I don't know if you can see, but you can recognize the manipulators. While you're modeling the low poly, the simulation runs behind. It's a tool that we wrote, so it's real time, shows you the shape of the fabric. So when you press 3, what you see is not related to fabric or anything, that's only an averaging process. So what we change the 3 button, so whenever we press 3, what you see is like a shape that the fabric would take if you stitched it in that way. Okay. So sometimes we make our own tools, sometimes we use existing. So this workflow is also, you won't find a textbook for this, it's just like our workflow. We take a low poly and we use the subdivision surface and move the points around until either it becomes completely flat or it becomes like fabric or like paper or like metal, so we can construct it from either fabric or metal or so on and so forth, right? The same way you've been doing modeling stuff, and then you've been converting it into a high resolution mesh and then cutting it up. Sometimes we add an intermediate step, you convert into subdivision, move the points until some geometric properties are satisfied, which makes construction easier. Okay? So, and you will see, so like that tool, it wasn't used to construct this building, but it's almost a direct translation of your Maya surface. That the pipe is your boundary, and the fabric is stitched, And there are 2 layers of fabric, there's insulation in between, and how do you bend pipe in 3D, you need a machine and so on and so forth. So this building costs like maybe 12 million pounds to make. It's a restaurant and an extension to a gallery and so on and so forth, which I showed in the presentation in the first day. I think 12 million, I don't know. But we took the same idea and like we tried to do it in India, like so we get an intuition of how those things work, right? So the red lines, instead of using a complicated CNC machine which costs like lots of money, and also we had only 1 layer of fabric, and because we did this in India, like we unrolled it and we gave those patches literally as one-to-one drawings. It was like many A0s. Each one of those strips was maybe as long as this room. And we gave it to a tailor because in India there's like very good tailors, right? And the tailor's shop is like this big. So he doesn't know what he's stitching. He's just stitching like this, and he folded everything up and carried the entire thing onto site, and we unfolded it. The pipes were bent on site by using gas welding, I don't know, heat guns, gas heaters, and you melt the metal a bit and bend it. And then we installed and then stretched the fabric, and then within a day, actually within 6 hours, we have that shape on site. The pipes took like a day and a half to bend. The fabric, the guy stitched it like in like a day, 6 hours of installation, and we have the shape on site. And then again, we didn't make any drawings to specify how to lay out the rebar. There were no drawings for the rebar, barely any drawings for the fabric. The only things that needed drawings was the location of this foundation here and there, and how to bend the pipe, right? So you had to give heights, and they drew it on ground and then bent it, and then we installed it, right? For the drawings, the reason why we didn't need drawings for these rebars is, again, we thought of a rule. We said to the workers, we already have this pipe here, divide the pipe equally, and then just take the steepest path down. Because we had the fabric, we had the pipe, and you have these bars, you can see where it is steepest, and then they just placed it. It's pretty accurate to where reinforcement is actually needed. So part of design and construction is also thinking, are these drawings necessary? Right? So it's like, what information does the worker need? What information does the contractor need? What information does the fabricator need? What information does the tailor need? They can't even understand, at least in India, they can't understand a plan. What they can understand is like, if you talk to them in their language. So for the tailor, we like literally drew it out in 1-to-1 scale. For the pipe bender, we gave him a 2D drawing and so on and so forth, right? Like, so drawings are not, so it's the same. This project, in our minds, is the same as this one. It was equally enjoyable, equally challenging, and equally kind of expressive. And the other thing is, like, it gave us this particular project gave us real intuition of how structure behaves. So, for example, like this little bar here, it looks like it's not important, and we thought it's not important, and we cut it. And then the 2 tips kind of came down by like 2 centimeters. And then you can imagine you're holding something together here, and you cut that, like it's going to fall over like this. And that's exactly what happened. So once we cut it, there were little cracks that appeared over like a week or so, like it appeared like this. It wasn't fatal, but it's still standing. So it kind of gives you these intuitive ideas of like how structure behaves, how material behaves, how these curved geometries actually behave, right? Okay, so that's on the side of like construction, but we're also interested in like understanding curvature more mathematically, for example. Like, so this is a project of my colleagues when I studied in the AA. It's a team called Why Me. So they were exploring like these mathematical geometries and how we can appropriate them to make buildings and so on and so forth. But if you notice at the bottom there's a set of equations that pop up, right? So that entire surface is described by this like silly long equation, which is useful if you're a mathematician. But if you're a designer, you're using that as a reference and you model it. Then you understand it like the way you understand it. Like it's the same surface, but you understand it intuitively. So things that you've been doing, like modeling by low poly. There was another project in the same year, again my colleagues at the DRL, at AA. They said like, no, we don't understand the equations, but we can generate equally fantastic surfaces, crazy, just by modeling in Maya, and that's what they did. So lucky enough, like for us at ZHA, like these two teams had already done it in 2006. So we combined both of them when we had to design the gallery for mathematics in 2014. So on the one hand, we explored use of the equations to generate all these variety of shapes, which would be very difficult to model by hand. Here, you just by changing some numbers, you get like very different surfaces. But that doesn't make it's very difficult to adjust it to fit a space because it has its own logic. Like that equation doesn't care whether there is a wall in the middle. It doesn't care if it's 1 meter or 2 meters less. But we, as designers, we have to care about that. So that's why we combine these two methods. One is used to explore, other is used to make it specifically architectural, right? Another area we're particularly interested in is this idea of origami, and more specifically curved origami, right? Origami, you know, you make a straight line and you fold it, right? Interestingly, the same thing works if the scoring is a curved line. And you will see the dotted line is a curved crease, and it produces curvature for free. You can start with a sheet material, score it, and fold it, and you get a variety of parameters, right? Like by changing the curvature of the curve, you get very different family of like weird creatures, right? So those are the parameters: the number of holes, where you put the holes, where you put the dotted line, and you get a full family of let's say objects, but they're not objects as designed objects, they're just geometric objects. Yeah, I went on to do my MPhil in like trying to do that. Physically it's like so simple and intuitive to do. Trying to do that digitally was like almost like next to impossible. But it took like, in the end we did develop some tools to do that kind of folding in 3D in a digital environment. And in 2012, I think, we made this sculpture in India, like first by making paper models, and then just literally unfolding the paper and drawing it, and then scaling it up in metal. So this was not drawn in 3D, and it wasn't even drawn in 2D, like we just scanned that piece of paper and scaled it, right? sometimes like when machines are involved, like the geometry needs to be digital, and this is what we are working with a company called Odico, as you see here. It's a company of 2 architects and 1 engineer and 12 robots. And they set up the company in like 2012, 2011, and 4 years later they're producing formwork for offices like ZHA, like they're making work for Siemens, they're making work for like big turbines and so on and so forth. So 2 architects, engineer from ABB Robots, and some investment, and they have a successful business, let's say. But we are interested in this hot wire cutting, as you will see. Also, that's why we are doing this workshop. We want to explore the geometric and design possibilities of hot wire cutting. It's not that we want to set up a business in hot wire cutting. What we are interested in is like what can that process give us as designers? How can we manipulate that process? How can we understand that process so that we can design better? So, how can we gain an advantage against Fosters, for example? Like the more we know about the process, the cheaper we can make, in one sense. On the other hand, we can do more, we can express more things. So this is the rough distinction between, if you don't have hot wire cutting, the other way to do it is like take a mill, like a router, and scrape off everything that is not, like a sculptor would. Take a block of stone and chip away everything that's not the sculpture. That's the comparison. If you use a hot wire cutter, the same surface can be cut in 1.8 minutes versus 3 hours and 34 minutes. So that's the increase of efficiency is like, I don't know, 100-fold. And these are not trivial, so this is not our building, of course. This is Noheta in San Francisco. All of that facade they milled it out. But if slight changes in that geometry, you could have hot wire cut it. And that would have made a lot of difference, right? So, and then this is the kind of thinking, if you have control over your geometry, you have control over your expression, you have control over the budget, you have control over how people navigate the spaces and so on and so forth. So that's why we are fundamentally interested in geometry, because that dictates a whole range of other things. Okay, so this is our building in Dubai, which is under construction. So all these curvy panels here, even though it's going to be made of glass, you need to make a mold into which to cast glass into. So the surfaces are modified slightly so that like it can be cut by a hot wire. So you can imagine not every surface can be cut by a hot wire, right? Like it needs to be straight in one direction. So we are also building these kind of tools, not because we want to do workshops with them, but because we want to know before we send a geometry to companies like Odico whether the robot can actually cut it, right? So like every arm, like the robot cannot reach every position in space. So if that's the cut we want to make, we want to know that how long will it take for the robot to do that path, and so on and so forth. So so on the left is our software, on the right is robot software that, as you saw yesterday, right? So and that's in Maya, and that's in like unusable engineering software. So we're producing these kind of benches with Odico. So this is going to be formed by by hot wire cutting foam and then casting concrete onto it. Casting concrete, every culture is like super experts at like casting concrete, like, and I don't have to tell Brazilians how to cast concrete, right? But like making the mold is kind of interesting. You can see here, I don't know if it's visible, there are these straight lines. That's the line that the wire passes. So that's the path of the wire. And you can imagine like this surface is a wire that goes and cuts it out. So moving on. So these are other technologies we are particularly interested in, like things that save material. So here, it's a technology called topology optimization. It removes material from where it's not needed, similar to our bones. Our bones are not solid, right? They're thicker in some areas, thinner in others, based on the way you run or the way you walk. So it's a similar technology that removes material from where it's not needed. We develop these kind of workflows, again within Maya, to convert that engineering information into actual 3D printed parts. So it's still not in production yet. These are all prototypes. You can't still sit on it because there are various issues. But we're already in like the 4th prototype. So soon we hope we can commercially sell them. You can't sit on this, that's why there is a tape, if you notice. But we are pretty convinced that we can sit on the next one. So with 3D printing, you can also manipulate color. And so the white areas are the stiffest, the hardest, and yellow is the softest. So like bone, like it's not all equal density, it's not all equal strength. Some areas are hard, some areas are soft. That's why when you land, when you jump, like the shock doesn't go through your body, like as much as it would have if you drop if your bones were made of titanium, you would feel it in your skull. Every time you walk, you could hear it in your skull, right? So it's a similar thing, like multi-material printing is quite an exciting thing for us because it allows for differentiation of geometry by structural performance. And currently this technology is unfortunately used to make like silly things like this, like a chess piece, like a cycle chain, and iguana. What's interesting though about this technology are these pins here. So it works like a traditional 2D printer, like dot by dot. So it puts a little bit of material, like a nozzle like this, and then shoots a little bit of light. So that's how the material gets hardened. So it's a liquid material that goes through a pixel and a piece of and a gun, a light gun that hardens it. So, which means you can think of resolution how at the level of a pixel. You can control material properties at that micro-millimeter scale. So here, like the only thing they're changing is yellow, the color, but yellow could be a soft material and blue could be a really hard material. So you can make up your own materials in this way, right? Like, so it's still very early technology. It costs a lot of money right now, but sooner or later it's going to become much cheaper, right? So, and the other thing is it fundamentally changes how you design. Because it's based on pixels, you can do your design in Photoshop. And that's why you can now import OBJs into Photoshop, and you can control material properties at the level of pixels. So it's like a stack of pixels. So at every layer you can say red is hard and blue is not so hard. And this is not some like science fiction technology. You can from Photoshop, I don't know if you have the latest Photoshop, you can order a print. You can import a OBJ and say, I want this printed, and it will submit a print, and a week later you can get that print. And it will give you a cost. I don't know if you can see very clearly. It will give you an estimate of how much it's going to cost. I'm not sure if it's available, the service is available here, but it's definitely available in many countries, like including the US. So, and that's kind of exciting because it's you can then make a design and send it to your wherever, and they can get it printed. Right? But for us, the interest is it fundamentally changes the way you design. So you're not modeling, you're not simulating geometry. What you're in this simulation, all we are controlling is a density of material per pixel. So what looks like a solid block is divided into very tiny little cubes, and we are saying controlling through an algorithm whether it should be blue or white. White means zero material. Blue means zero material. White means solid. Right. So you're changing the way you design based on the technology and the way the technology operates. So, for example, currently, if you had to print, how many of you have done 3D printing with the MakerBot? So you have to give it an STL, and then it will STL file format full of triangles, and then it will cut it up into layers, and then like it deposits material. So that's a different printer compared to this one. So that one needs geometry, this one doesn't need geometry. In the traditional sense. It doesn't need a mesh, it doesn't need NURBS. All it needs is a stack of images. So you can design in Photoshop as a stack of bitmaps. So another way to think of the stack is a time. So if you have a simulation that grows, time 0 is at the bottom layer, time 100 is at the top layer. So you will naturally see kind of like this. Right? Like you don't have to cut it up. You just paint these layers in Photoshop.
Do you have tools to export from Maya, for example, to this kind of thing?
Yeah. I mean, you can import a Maya object and then convert it into this. You can do that in Adobe now. Like you can import OBJ into Acrobat. And the same way you can print it to a 2D printer, you can send it to a 3D printer.
This is like normal mapping, right, for rendering.
No, it's not like normal mapping because normal mapping is only on the surface. Here you need information at like every slice, at every pixel on every slice. So it's not only on the surface, it's through. Make sense? So imagine like this is a grid. There are little cubes here, and you're controlling the color of that cube. So it's the same idea of pixels extended to 3 dimensions, and it's called a voxel. A volume pixel is called a voxel, right? Okay, so similar technologies at architectural scale, like this is a thing that we did in Mexico City. Can you guess, now that you've done Maya modeling, how many faces that thing has? 4. Who said 4? 4? What are other guesses? 6? Yeah, it is 6. I mean, that doesn't account for all those little, and this is also rain flow, right? Like, you can imagine water going down. So we try to use topology optimization at architecture scale. Usually it's used to make small little brackets or things that go inside of aircraft or like these kind of things. No one's really tried to use it at architectural scale. We thought, we give it a try. First we made a model by exactly this way that you have done. And that's Alicia's hands. I can't make a model to save my life. But it's a scaled idea, so if you can make a model, you can scale it up, do it in foam. Instead of a laser cutter, you use a CNC router, and then you put rebar, put concrete. Within a week you have something that, touch wood, it has survived two earthquakes in Mexico City. It's about 4.5 meters tall, and the foundation is not that deep, it's only 40 centimeters deep foundation. Okay, I'll skip through this, like this is like what we do on a Sunday. But doing that on a Sunday allows us to do this on a Monday, right? Because this is what excites us, like the drawing, its impact on like making design outcomes and controlling our geometry, controlling our design output. That's what excites us, but sometimes we have to, do things which are not natural for us, read these kind of papers, and try to make sense of those symbols so that we can then at a later point be able to control our design a whole lot more. So here the tool is very simple. Given the red input lines, so it's a tool that we built. Given the red lines, it produces the black lines. The reason we needed that is to use it as a navigational device in the gallery. So the lines naturally lead people through so you can see the 6 divisions, 1, 2, 3, 4, 5, and 6. Those are the 6, you can't see them, but imagine them when it gets darker. 1 here, 2, 3, and the mirror. It is a gallery which has 6 zones. There are 6 stories to be told by the object. There are 110 objects. It's a gallery for mathematics, and so the curator wanted it divided into 6 zones, and we didn't want to make 6 rooms. So so those red things are the benches you saw previously, and the floor pattern follows the benches, and the ceiling follows these zones, and so you can achieve the same architectural intention as 6 separate rooms, but by just reinforcing the information in many different ways. On the floor, as furniture, on the ceiling, as lighting. Each of the zones have slightly different light because they are slightly different objects, so on and so forth. Okay, so that's one of our main kind of design intention, not to make boxes and like cut off things. At the same time, we also don't want complete open plan, because it's like you can't function in an open plan. You need some kind of divisions, right? So some of these tools are usually used in the computer graphics world to, I don't know how many have seen like the Life of Pi. So the tools are usually used to make hair on the face and fur on the tiger and like these kind of things. We use the same tools to make these patterns on the ground, or same kind of mathematics. So you can imagine when you comb like hair, it all aligns in a kind of smooth, flowy way. So that's why we are looking at tools from the computer graphics industry, sometimes from the engineering community, and so on and so forth, to then use it in a design way. Okay, so I mean, these are not tools; these are like kind of research areas in places like ETH and Cornell or Stanford or wherever. So the beautiful thing about internet is it doesn't matter whether you are in the UK or in India. You have access to cutting edge technology. All you need is to spend some time and understand those things, right? And you can use them in many different ways. Okay, machine learning is like is a thing that Google does to run your phones and for Siri to answer your questions. We said we want to look at using similar technology to understand our own models. So it's very early stage research. What we are doing is this is not ours, of course. This is from ETH. You feed the computer a bunch of models that you have generated. It puts it in a blender, analyzes it, and then the next time you model something similar, it will start making suggestions. It's like, this is what you did 30 days ago, this is what you did 5 days ago, like, do you want to do this? Like similar to autocomplete on your phone when you're texting. It's a similar thing, but for 3D geometry. Right? So it's a kind of exciting use of technology that was originally meant for your phone, but applied to 3D geometry. So these kind of 3D applications are of interest for us as well. There's a thing called parallel computing. How many of you are aware of parallel computing? So I think that image kind of perfectly explains what parallel computing is. You can divide the task into multiple processors, like your rendering. Like when you use V-Ray, there are six dots that are going off, which means 6 different processors, 6 different little chips on your computer are doing the task simultaneously. So in theory, you can distribute work to thousands of computers, but in actual practice, that's the mess you get, right? Because you need to coordinate 1,000 dogs, and you need to collect information, and that's why sometimes your render fails. Like a render farm, some of your computers might fail, and then the entire render fucks up and stuff. So we do have some active interest in these kind of technologies that make our life easier. Machine vision, so on and so forth. All of this, again, more applied to what we are interested in, how all of that helps us design in the virtual world, like with VR. Not only as a presentation tool, but also to explore how virtual spaces can be different, right? Like gravity can be upside down, it can be sideways, you can have infinite friction or zero friction. So those are exciting kind of things to do in the virtual space, which you cannot really do in real space. So all of that technological research or interest is ultimately geared towards something which is a design output. Okay. All right. So I got 3 minutes. I will skip through the basic. So that's more or less the main research trajectories that we're currently been doing over the last, or currently doing over the last 6-7 years. And other main interests include, as I said, connecting back to historic methods of design. So this is a method of structural design which was used to design bridges like these. But the interesting thing about that is it's not numeric. It is purely geometric. So if you have a drawing board or AutoCAD or Rhino or whatever, you can design the shape of that bridge and also dimension the bridge accurately with just drawing tools. So it's an area of people like Gaudi also use these. Actually, Gaudi used this method more than he used the hanging chain, because the hanging chain is not easy to calibrate. But this method is very flexible, and lots of designers in 19th century France and also Britain used this graphical method. It's called graphic statics. Right, so Gaudi used it to design that wall, the supports for the tree-like supports, and then the King's College fan vault. And so my PhD advisor and his research professor Philip Bloch in ETH, they've been taking these and making it these methods, which are originally two-dimensional, and extending them for use in the computer and also for 3 dimensions, to make these kind of structures. So interestingly, as this model shows, this stands entirely in compression, and there's only like a tension tie here, like a cable. I don't know if you can see, there's a hand trying to cut it. So that's why as soon as you cut the cable, everything collapses. So it's a demonstration that it is entirely standing on compression, and the benefit of structures that are purely in compression is that they can be much lighter than structures that require to resist bending, right? Like your table or this, it resists bending, means there is more material here. But if the structure cannot resist bending, but it's only purely in compression, you need to have less, you can have less material. And we've been working with his group to design things like these structures, which are a combination of historic ideas of balanced spiral staircases, arches, and we hope to build this. Currently there's not money for this, but sometimes soon enough we hope to build this kind of compression only structure in stone. Again, instead of cutting foam, we're gonna plan to cut stone. Okay. So the rest, I think I will stop here. So there's like, as you can imagine, this is a presentation I made for all of the offices, what we've been up to over the last 9 years. So it's a pretty long presentation, but maybe we can continue this during the rest of the days and combine it with Alicia's presentation and David's and so. But skipping to the kind of end. Yeah, so as I started, Maxi took 10 years to build from start to, 10 years from inception of design to actual completion. It stopped twice, and it opened in 2012, I would say, or 2010. Baku took 7 years from design to completion, completed in 2014. 2014. But the interesting thing is it's a generation of architects, and you can tell the difference between that language and this one is not dictated by ZHA, or wasn't dictated by ZHA, or not dictated by Patrick, or it's dictated by the interest of the people joining the company. So people join when they're like maybe 20, 25, 26, and 6-7 years later they get to see one of the buildings they worked on, and obviously it will be different, right? Like, because the tools we are using are different, our cultural references are different, technology is different, society is different. So you get to see differences like this. It's, some people say that is old school ZHA, they like that one better than this one, and some people think that's too formal, or this is too formal. It doesn't matter, internally, at least for us, it doesn't matter. It's all continuation of like a series of ideas that come from groups of people who joined the office at similar times, and they grow together, and hopefully, like in just 5-6 years time, they see their first build project. I've been in the office 10 years, I've not seen a single build project yet. But at the end, in December 2016, our gallery will be complete. So that will be the first complete design build project, which we made part contribution to several projects, but like it's one of the so this will be complete by 2018 or so. But you can see that this is a completely different language. I don't know if you can see, but we think it's a completely different language to this, a completely different language to that. And once this is complete, it will be a kind of the first major build project for code in a sense. So and it's a journey that starts 6-7 years ago, like interest in shell geometry, and looking up historic methods of how to design shells, finding other people in the 60s and 70s who did it, including Niemeyer and Dieste or Candela, and how did they do it, and so on and so forth. It's a very fascinating world, an exciting world to go into, because we know at some point there will be a build project that represents your interest, right? And that's okay. So that's I will stop for now. Let's just leave this video. So I hope you kind of see value in pursuing something for many years, be an interest in modeling or mathematics or art or working with artists, looking at other industries like computer graphics. So never dismiss any avenue. Anyone who's working any other field, like there's something that you can learn from them. And it's not that like we had a game plan like 10 years ago that we will do exactly all of these things. So every year, this year robots interest us, we will do robots. Next year, maybe it's something else. But the spirit is the same, like always be experimenting, always be inquisitive. And there's no reason to feel that some countries have more opportunities than others. Like there are different opportunities. So most of the tools that are used in the design of this one you've already seen in the last 3 days. So it's not so much about tools, it's about practice and all the other background research that really makes a project.
And to simulate that material
Stretching?
subtractor, how it's in Maya also.
And well,
Really?
I mean, that's not what engineers use, of course, but it's so the shape that we generate is very close to the actual engineering shape. So it gives us enough of an idea of whether my head is going to hit it or not. So it's plus minus 5 centimeters. So poly modeling, end cloth, laying out the hot wire cutting. We're going to see like some of the benches in this project are going to be made by hot wire cutting and casting in concrete. Boxes, we all know how to make boxes. Yeah, so it's a gallery that's going to remain for 25 years. So it's strangely interesting for us because it's a gallery for mathematics and computing. So there are 110 objects in 85 groups, and each one of them has like a story which is like super fascinating. Like there are things like instruments that were specifically made to measure the area of like leather. So once you take the skin off of a cow, you want to measure how much surface area there is. So there are instruments made in 16th century that will accurately calculate surface area of leather or textile. And then there are like new things like the first Macintosh computer. So if you have a chance to visit London after 2016, I would say definitely go here. And if you have children, or if you don't have children, if you have young cousins and so, like ask them to go to not only this gallery but the Science Museum is a fascinating place. So, questions?
The fabric that you used to build that shape which fabric it is?
The same fabric that you use for tents, making tents, like camping tents. Yeah.
And then you just put the wires and concrete.
Yeah.
Directly. And how thick is it?
5 centimeters.
And something waterproof?
It's outside. We don't. Yeah. We didn't have, it was made out of workshop budget, right? Like, so we didn't have money for waterproofing or anything. So if it falls down, it falls down. Single size. No, so you have fabric only as a guide. You put the steel and then stretch I don't know, it's called chicken mesh. It's a mesh with the holes in it, hexagonal holes.
Cara de galinha.
Yeah. And it sticks. It's between the fabric and the chicken mesh.
But that other one with the restaurant looks like has something to what. Of course, there's something waterproof.
Yeah, well, yeah, that one is fully waterproof on both sides.
It's like a folded shape, actually. There's some.
Oh, yeah, the
some
exterior.
marks,
Yeah, the exterior is covered in metal. Only the that one. Yeah, so
It's metal.
up to the glass is a metal. It's to cover the pipe, but everything inside is fabric. So it's yeah, you can see. So the metal piece is to cover this structure, and that's all fabric. So that's 2 layers of fabric, and there's an insulation layer inside, and the fabric is waterproof on the outside. But they spray something like a Teflon. It's a Teflon coated fabric, like the Millennium Dome. Yeah.
Another one that you should you have the foam. You have the foam, and then you put it slice by slice, and then you fill it with the concrete.
Yeah.
Right?
That was poured from the top.
And then you wait and
Yeah, because foam is hard enough, like so you can compact it. So because fabric, because it was stretched by hand, it's not hard enough, so you have to hand render.
The ones you did in India and Mexico, there's something that holds the concrete while the caption, so it doesn't deform your shape. I don't know.
Yeah. So after this layer of reinforcement, you put chicken mesh, that thing that she said, and then you slap concrete by hand.
And below that chicken mesh, there are some supports that you remove after the concrete is dry.
No, first you do the top layer, and then remove the fabric, and then
Oh, okay.
slap concrete like this. That's I don't know how it like concreting is done here. For thin amounts of concrete, it's called ferrocement. Like it was invented by how many of you heard of Luigi Nervi? Nervi? Yeah, Luigi Nervi invented this just after the war, precisely to save the amount of concrete, because there was not enough concrete in Italy. So he made this chicken mesh thing, and you hand
Mhm.
it has good strength. There are flyovers made in this way.
And the big projects from code that it's not ready. What's the main material?
Concrete.
And it's painted, but have the yellow colors.
No, it has tiles to for reflection and like solar. How to say? It's like the Barcelona tiles.
Ah, okay.
To prevent gain of heat. So you have reflective tiles, so it bounces light off, which means the inner surface of concrete is cooler than. It's a ceramic tiles that are mounted on top of cable net on top of concrete surface. It's actually not tiling, it's a ceramic facade on top of a concrete. It's the same as, I don't know if you have seen many facades, glass facades are now made of cable net. So you stretch cables and hang glass off of the cable. So it's a similar principle. So it's kind of like a fabric made of tiles.
For example, in Maxi,
Mm-hmm.
you said it took 10 years. Did you spend a lot of this time making the approval?
I mean, I didn't work on Maxi. I'm just telling you. It started before. The design of the Maxi started well before I joined the office in 2007. But 10 years. The interesting thing about Maxi is like by the time it got built, like the people who joined the office when it started, half of them had left, and so they were like, and it stopped like twice for planning approvals, for lack of funding, like some protests and stuff like ZHA building will never go up without protests. But yeah, but nonetheless, whoever stuck around like got to see a pretty unique building, I would say, start to finish.
People who approve projects in the countries must love you a lot.
Well, it's both ways. It's not so much like yeah. As I said in the beginning, like it's not that just because we are ZHA, like people are throwing money at us. Like you have to convince them, and you have to. There are lots of ups and downs. It's not blue sky at all. Yeah. And in many cases, we even have to. We lose projects just because we are ZHA. It's like, oh yeah. Any other?
What were you doing before 2007?
I graduated from architecture undergraduate from India in 2002. 2002, yeah. 2 years I worked for my father, 2004. Then I did my master's at the AA. Worked for about 15 months at Populous. They do stadiums. And then I met Patrick in a random party and joined ZHA. Well, actually, no. In between, I went back home. I thought I will go back to India, but then I came back home.
So like the whole
Right now, 7,
So like,
other than me.
and like it's divided like in teams, like each team gets a project. How does it work?
Is code divided into teams?
No, the
Office.
Like, the
Yeah,
code is one of the teams and
Yeah.
focus on like finding shapes. And,
Yeah, yeah.
and
The office is divided into teams, yes. So there are 3 major teams, well not teams, there are 3 major groups called clusters. Each one has about 100 people in it. Within that there are teams of like maybe 6 to 15 people, each of the clusters. So, and whether it's a small project or a big project, initially the design happens only between 2 to 3 people. So whether it's an airport or a house, it's the same number of people who initially work on it. And yeah, the airport tends to need more people as you go. But,
And ZHA was part of this team or this process? He was sketching
no.
or?
well, I mean, I guess, I don't know, like, not since the time I joined at least, like when the office was much smaller at 7 to 10 people, maybe, maybe she was more involved, like by making paintings and drawings, and at least, that's what Patrick says. I don't have any direct knowledge of it. That she was more involved in the actual drawing of plans, and not plans as a technical drawing, but plans as a method of designing. But no, once you grow beyond a certain size, it's pointless for ZHA or anyone who runs the company to be involved in design, because you can't micromanage 200 people, or you can't even micromanage more than 10 people. It's very difficult, so it doesn't make sense for her. So she was involved in like the overall directions of the kinds of teams she made, and like collaborators she brought in, clients.
She was approving or disapproving?
Yeah, she was. Yeah, in that sense, she was always involved, like approving, disapproving projects, or mostly disapproving. She was a spirit of the company, like let's say, and more, not the everyday. Okay, put some video. This is a project that we did. So this was a DRL project that using a laser cutter, you remove some material and therefore you can fold it in. So it's plywood, right? Like, or MDF. You laser cut those patterns and you can fold it into different shapes. And then we decided to use that technique, but there was already a company in Germany that does that. So you can fold MDF into these loops by cutting material like this. And so we use that techniques to make all of the loops and join them together. So again, this entire pavilion, everything was made in a laser cutter. I mean a big one, not this same size. So you can see topology optimization just to get the pattern of where the structure needs to be. And then we converted that into a mesh, like by modeling, low poly modeling.
In this case, the red represents
The most force, the area of most stress. So where there should be structure. And then we made these custom tools so that so we move the points around until everything is flat, so we can then laser cut it. So if it's twisted, we can't laser cut it, right? So then we digitally make them flat by moving points around, and then everything can be manufactured in a laser cutter. So, which means you have to unroll everything flat, and then all the boundaries are cut and everything, all the laser etching is done, and then you fold it. So this is the underlying structure made of aluminum box sections. And the loops are made by folding plywood, MDF. And the cover plates is made by folding steel plates, also by taking flat sheet metal and then folding it, or bending it rather. And the lures are cut again, CNC. So interesting thing about this is that it was one person designing it from our end, and one person from the fabricators and doing everything digitally, and the machine doesn't care. So the assembly was a team of 15, but the design and production team was 2. So you can see all the parts are cut, assembled. Also, a kind of interesting story. This factory is in like the middle of nowhere in Germany. It's a village of 1,000 people. They had space. They have bought some machines, and they're doing projects for Shigeru Ban. They're doing projects for ZHA. They're doing projects for well, like really big companies, Jean Nouvel.
They bend the plywood.
Now they bend plywood, they bend everything, anything that is flat, they can bend. Yeah. They can bend sheets, metal, fabric. So that's also very interesting, right? Like, you just need to invest in these machines and you can do exactly the same. And so technology is so transferable. Like if you get like one investor, you can buy a few robots, like the Odico example. They bought second-hand robots from the car industry. When Denmark stopped in the 2008 crash, of course a lot of car industry in Holland and Denmark like kind of died. So they were giving away robots for dirt cheap, for like 2,000 pounds, 3,000 pounds. So they went and just bought a few robots, got an investor, and then set up this company. So there's definitely a lot of scope to do stuff.
Where is this project going?
It's currently in the Philippines. Yeah. I don't know, they gave it away in some AIDS charity or something. So I don't know where it's going. Well, actually, this one is going to go to Syria. Also fabric. You know, we studied like the same kind of bus stop module system. So I guess I showed this. So these are Syrian children of refugees. So that's the render and that's the physical thing. This was entirely fabricated in Turkey. Also in the remote part of Turkey, not Istanbul. Okay. All right, so we get back to designing. I would say